Hello again, folks. I'm going to do section 7.2 and I'm going to try to do section 7.3 actually, so we'll be a little bit ahead of schedule. There's basically some formulas and identities that I'm going to have you look at. Basically, there's a form I had designed which will be available again in Canvas that looks like this. So if, while I'm talking about this, you want to print this out and fill in this table as we discuss it. Okay? That's basically section 7.2 with 7.3 together. Okay. Now, let's see, I'll label this 7.2, 7.3, which is about right triangles and unit circles. Okay. There we go. Something like that. Gotta get new markers already. It's running out. Alright. I should put my eyes on here. There we go. Oh, there you are. Okay. Sorry. Alright, anyhow, let's start with right triangles. There's basically three perspectives for a right triangle. And remember, a right triangle is something that would be identified visually, at least, by a little box drawn into one corner. And I've seen some math tests and some textbooks that are a little lazy, and they neglect to do that. The math person worth their salt, at any rate, should always put that box in the corner to certify this is definitely a right triangle, unless they're asking you to prove it. Right, anyhow, there's three different ways that you might refer to them, or three different perspectives that they will be referred to from. Let's just say there's a traditional perspective, which you're already familiar with. There's the 7.2 perspective, that's section 7.2 in our book. And there's the section 7.3 perspective. Right. The traditional way of looking at a right triangle, referring to it or utilizing it somehow, would be via the Pythagorean Theorem. Right. And the Pythagorean Theorem, remember, famously is the sum of the sides squared is equal to the hypotenuse squared. The sum of the individual sides squared each. Okay? This will be adapted for our purposes also if we translate this onto a coordinate plane. Here's a drawing also to summarize. If you have a right triangle again, here's my box. Setting a good example. The one thing that is non-negotiable is which one of these refers to the hypotenuse. Remember, the hypotenuse is the C value in the formula, but in the picture it would be this dimension. Hypotenuse is the Greek word, I believe, for longest side of a right triangle. All right, and you could identify it, as long as you have a picture, by just looking for where the box is and then just noticing that it should always be directly across from that, this dimension here. All right. The other two are usually referred to as a side or leg. And you could call either one A or B. That is to say, you could call this A and this B, or this A and this B instead. All right. My logic is, well, be consistent. B is in bottom, shall we say, and A is in altitude. Altitude, not altoid, sorry. It's minty fresh math. Altitude. And it would be this dimension here and this dimension here. The hypotenuse would be C again. Okay? That's more or less what we're all used to. It's completely dry. It's gonna go. The other two, the ones that are really the other two perspectives that are really the subject of today, I'm just going to abbreviate that, HIPOT. HIPOT. The perspective is in relation to a central angle. If this is in relation to the Pythagorean Theorem, then section 7.2 has the perspective of our right triangle in relation to a central angle. Remember, if you have a central angle, that means your vertex would be, if it was superimposed upon a coordinate plane, it would be at the origin. Anyhow, it would normally, a triangle would be oriented like this. And again, to be a good guy, I'm going to be consistent and put that box in the corner. Emphasize that this is a right triangle strictly. And these sides, what are normally a leg, and a hypotenuse, have different names or different labels. They're the same thing really, but for our purposes in section 7.2, we'll call them this instead. In respect of some angle that would be here, and I'll put the little Easter egg theta symbol here to represent an angle. In respect of this particular angle, the side that is across from it is referred to as, I'll put this in a different color, opposite. Which makes perfect sense. It's opposite of the angle. Right? The side that is immediately adjacent to it here is referred to as adjacent. Kind of giving away the score here. Adjacent as in next to. One thing that is consistently true is the side that is across from the box in the corner is still the hypotenuse. Again, that is always non-negotiable. Okay? So when you're doing any sort of work, and again, this would be in my open math, section 7.2, just realize that these are what the labels will be, potentially instead of A, B, and C. Okay? And then for section 7.3, be consistent with this, the perspective switches again to being in relation to unit circles. A unit circle, I think I may have mentioned this momentarily in the last video. A unit circle is a circle that has a radius equal to 1. Okay? And in this case, to draw it on a coordinate plane would be practical, but I'm going to try to simulate that here. You know, cheat, I have something of a seam. Bloody murder. Alright. Here is a badly drawn circle. I'm setting myself up for failure, I really shouldn't. It's okay. If you can imagine that the radius of the circle, which would be from the center out to the edge, as being r equals 1, you have, by definition, a unit circle, right? You can relate a right triangle to any one of the coordinates that would be an x value and a y value that make up the edge of the circle. They would all be derived basically from r equals 1. Now, imagine this. If you had a right triangle that connected to the center of the circle, down here to form a right leg. If the whole distance from the center to the outer edge is equal to the amount of 1, what you would probably expect is that this would be shorter, right, to some degree. And using these relationships, basically it could be calculated. Turns out that, I'm going to erase this just because I need the space. If you wanted to determine the length of this segment of this leg of the right triangle, which would somehow be smaller than the amount of 1, because 1 would be the whole distance, and this is something shy of that, it actually comes from this calculation. X is equal to r times the cosine of 30, of theta. Jump on the gun here, 30 is a specific angle. This is a generalization. Anyhow, if, and incidentally, I'm kind of still jumping the gun. If you're a little intimidated by cosine, which is what COS stands for, don't be. All right, we're going to go into it in finer detail in a moment, but it's a trig function. All right, basically the radius times a trig function of the angle, right, which is really just a ratio. It's a glorified fraction. The value that would be here is a glorified fraction. All right. This would reduce, at any rate, if your radius is 1, to 1 in place of r times that trig function. And would basically be this. This distance for x would be equal to the cosine of whatever the angle is here. Okay? Similarly, and this is again a preview of section 7.3, which we're going to get into in a little bit, the distance or the length of this leg could be calculated by a y value. And the y value in relation to a radius of 1 would be equal to r times the sine of theta. That is the radius times a specific trig function and a specific angle here. All right. All right. Anyhow, again, if your radius is no bigger than 1, 1 times that would just simply leave you with sine of theta. Okay. Anyhow, this is basically how you would calculate the coordinates of any point that happens to be on the edge of the circle. Right? That is the basis basically of section 7.3. Determining what these coordinates are, realizing that you're going to be using a trig function in the process. Right? And the simplified version here for a radius of 1 is just simply y is equal to the sine of theta. All right. Again, if you feel a little intimidated, if you've never seen this stuff before, don't panic. We're going to go into greater detail in a minute. A finer detail, I should say. All right. This is just to establish an overview. Our perspective of a right triangle in relation to Pythagorean Theorem, more or less the usual situation. Our perspective from section 7.2 and our perspective from section 7.3. Okay? I'm going to erase this. I had to make a bigger board. I don't know if it's noticeable. The last one was unfortunately just a little bit too short this way. So I hope this is a little bit better. I try to aim the camera too. Let me prop this up just a hint more. I have my little pocket protector back here. Trying to keep it so that you can see the whole board. If it starts drifting again, yell really loudly, I can hear you, sure. Alright, in keeping with sort of an overview, let's talk about functions in general. A quick review of where we have been and what we're doing now. Alright. The most basic function is an identity function, in which case, just look at the unique feature that identifies the function as being the right side of the equals. All right. We had an identity function, the least complicated of all, in which the y value is simply equal to the x value. A slightly more complicated version of this would be something that is essentially a transformation. Now, we don't ever call it that, but when you had famously y equals mx plus b, you'd have basically the graph of the identity function shifted over a certain amount. It's plus some number. Actually shifted up to be more accurate, because this is a y-intercept. And if you had some interesting feature in place of the slope, as this is the slope-intercept form of the equation of a line, all right, this would cause the pitch of the straight line, which identity functions would produce, all right, being more shallow or more steep. Okay. And naturally we had quadratics, which is just changing this by upping the ante of the exponent 1 degree higher. Right? If in theory identity is degree 1, then we would have y equals x2, and we would have a quadratic or a square function. Okay. And again, you could transform this. You could add, put a simple number next to it, plus or minus, and it would cause the parabola shape to shift up or down the axis. Right? You could give it a coefficient to make the parabola a little bit wider open, or a little bit more narrow. And you could start to move it left or right along the horizontal axis if you group this into parentheses. Later on we had discussed y exponent of 3, and this is understood as being a cubic function. And also squares, square root rather, which is basically x to the 1/2. It's kind of disguised, because what is it really? 1/2 is really a square root, with the index would be normally written inside the radical symbol, just inside this little check mark. And whatever the top exponent is can be written here on the inside of the radical. Right, these are the same thing. Then we have the most basic form of a rational equation, which is a rational function, which is a reciprocal. Right. Let me just label this. This is square root. And this is, how do you call it? A reciprocal function, which is the most dumbed down, simplified, least complex version of a rational function. It's rational. It basically has this identifying line here, and the variable, which would normally be above the line, we just don't consciously pay attention to it in the most normal cases. X cubed, x squared, x1, all right? The variable is now below that line. And it could be, in theory, whatever exponent you put here. Let's see. Then we had absolute value. So if you had y equals to the absolute value of x, the absolute value function famously makes the V shape. And let's see, then we got into most recently exponential and logarithmic functions. So if you had y equals some base number, and now the variable is the exponent. You have an exponential function. And its its inverse, y is equal to the log of base b, so the x of x, the log of x base b equals y, right, which would translate to basically this situation. B to the y is equal to x. These two, of course, being inverses. Okay. This is basically where we're at as of this point in the semester. Right? We've covered basically these types of functions, and you know that they draw unique pictures, right? Anyhow, what we're going to do now is add the trigonometric functions. And there are 6. So just underneath this, let me draw that. I'm now, in theory, introducing you to the 6 trigonometric functions. Which are good to know, I feel, in a particular order. All right. Sine, cosine, tangent, cotangent, secant, and cosecant is what they're referred to. All right. The trig functions are basically ratios of the sides of a right triangle. Let's see if this, let me just check that this is in the frame of the camera. That's basically where they come from. It is good. The ratios of the sides of a right triangle. All right. I'm going to erase this, and then I'm going to pull up the, I'll ask you basically to pull out, or photocopy or print rather, this blank sheet that I would have given you in person. And we're going to fill this out together. And before I do that, let me complete this thought. This is logarithmic function, exponential, absolute value, reciprocal, rational. Reciprocal in this particular case, rational in general. Square root, cubic, square, all right, can also be quadratic if you have other terms here. And the identity, all right, which is also referred to as linear. All right, if it has the extra features usually, all right, plus or minus something. And a more interesting slope than just say 1 would be a linear function. Right? Identity is this specific type in the same way that square is this specific type. And reciprocal is this specific type. It's a subcategory, if you will, of each of those. All right, let me erase this. And I might even turn the board here. It depends on whether it's in frame. I have a feeling that if I do that, it's going to be out of the frame, but let me see. If I rotate this around, behold the special effects, folks. You're missing out here in my hallway. Gotta be cheerful, right? All right, that's pretty good. I'll try to limit myself to, let's see, just about here. Okay, I'll draw a line to remind myself. I'll go lower than that. Okay. If only I knew how to draw a straight line. Jeez. This is why I got kicked out of art school. Good. I'm obsessing again, but hey, something like that. Alright, just to sort of simulate the diagram that I would have given you, and this will summarize our trig functions. As similarly as possible. Okay. Number. And a column like this. Yeah. Sorry, it's faint. And. Oh, God.
Stop squeaking.
Incidentally, if you see any weird faces or spots here, right, in the camera, to make this board, basically I took wrapping paper that I had and I turned it backwards. It just happened to be white on one side. But it's snowmen. And you see the ghostly image of snowmen staring back at you. All right. There is famously this mnemonic device, all right, which is abbreviated as such, Sohcahtoa. And if you're doing any of the homework in section 7.2, right, it's really this this incarnation of trig functions that you would utilize. Right? It is good for basically triangles, right triangles, of course, in any orientation. And by that I mean you could have a right triangle drawn like this, more or less the standard position, you know, if there was a vertex here at the origin. Or you can have it like this, you know, as long as it's a right triangle, sort of rotated through the origin, right? Or something backward or upside down in free-floating space. All right, a freestanding, if you will, a triangle. Any orientation, I would use or employ Sohcahtoa. Sohcahtoa is again a mnemonic in which the initials refer to the trig functions. So let me do this. I wish my black marker wrote a little bit more darkly. Let's do this first one here. If you have the first trig function, which is, it's referred to as sine. And it would be spelled S-I-N-E. Right? But the abbreviation as a function would look like this. Sin. Right? And then, because it's a function of parentheses, I need a little bit of space, so what I'm going to do is I'm just going to erase this and scoot it over. So sin, parentheses, and then the ratio that it is equal to. Let me draw a triangle. Don't write this yourself on the form that you have. All right? I just want to refer to a triangle as I'm doing it. We had established before that the trig functions are ratios of the sides of a right triangle, and that the sides of a right triangle are referred to as adjacent, opposite, and hypotenuse, respectively. Okay. So you could glean quite a few ratios out of just those three labels. Right. The sine of the angle, that is the function of sine using whatever angle is in this corner, right? It would be written like this inside the function, sine of Easter egg, if you will, sine of theta, is equal to this specific ratio. The opposite, that's what the O is in so, over the hypotenuse. So the opposite side of this angle, right? Or in theory, if you had another angle here, it would be the opposite side would be here instead. The opposite of whatever the angle is, whatever the orientation of the triangle, over the hypotenuse, that's what the H is. So I'm just going to abbreviate this as op over hype. Okay. Then the next one, trig function number 2 is cosine. Incidentally, if you're wondering where these strange words came from, this is probably poorly translated Arabic. All right, now, algebra as a subject was introduced to Europe through North Africa, and the language that was used would be Arabic at the time, at least, and the language, the official educated people's language in Europe at the time was Latin. So the mathematicians of Europe, trying to catch up basically, would try to translate the Arabic text that they have into Latin, because that's the language that they learned in college. If you were going to college in the Middle Ages, you were guaranteed to learn probably Arabic, Latin, and Greek. All right. Anyhow, a sine, and you'll correct me if I'm wrong, is sort of a poor translation of a nerve, a biological, conduit, a nerve like in your body, which is, again, loosely translated to a chord, right? But this, again, all relates back to a circle, and there are chords of circles as opposed to diameters of circles. Well, a sine is a string, if you will. A chord, a nerve, whatever you prefer. Anyhow, a cosine, which is the next function, it's spelled C-O-S-I-N-E, and it is abbreviated COS, and then parentheses because it is a function, and then what that translates to in terms of a ratio, I'll write it here. Theta, again, this is in reference to an angle, and I'll erase this little bit of scribble that I've done here. The cosine using Sohcahtoa is this. Complete my little Easter egg here, theta. Okay. Cosine, C and ka, is adjacent over hypotenuse. So, in respect of a function that is a cosine function of this particular angle, it is adjacent, right, over hypotenuse. It's referring to these two sides, specifically the adjacent side and the hypotenuse. So I'm going to abbreviate that ADJ, and then again HYP. Co, this means it is the complement of sine. Right? Remember complements from angle relationships. Two complements add up to 90 degrees. Well, a cosine and a sine function are out of phase by 90 is what they would say. These produce waves as drawings. Right? Number 3. This is the third unique one. Everything else that follows is derived from these 3. The tangent. Tangent, again, probably a poor translation. Tangent is a type of line. Again, you don't have to draw this, but if you had a circle and you had a line that is right next to a circle and it just touches it in one location, they would refer to this as a tangent line. Right? It is tangent in one place. It touches in one place mathematically. Right. Again, you don't have to write this, of course, but a chord is a string, a line, a nerve, if you will. A sine is something that basically connects two places on the edge of a circle. This is a sine. Right? right? It's something like a cord, if you will, all right, a nerve. Let's see. A cosine, to complete this thought, is abbreviated tan. How to spell that? Lowercase, okay. Tan, I'm gonna make that an I. And it is this ratio. Tangent of theta is specifically, using Sohcahtoa again, the tangent toa is opposite over adjacent. That's the O and the A specifically. So, I'll do that again if I try. More special effects. Sorry. Opposite over adjacent. The ratio of these dimensions, whatever number is this respective of this side, whatever number is respective of this side. Opposite over adjacent. It is a glorified fraction. These trig functions, that's what they translate to. Okay. Now, let me erase this picture because I no longer need it. If you know Sohcahtoa, that the sine is the opposite over hypotenuse, the ka is the adjacent over hypotenuse, and the toa is the tangent opposite over adjacent, then you could infer what the remaining three trig functions would be. They're just the reciprocals of these. That's why I suggest that you learn them in this particular order, sine, cosine, tangent, and then when you're doing the next one, go for the mirror image. Put this here. The next after tangent would be cotangent. Maybe I'll put this in green if it writes. Yeah, it's pretty good actually. Okay. Cotangent. Again, co is referring to the fact that it is a complement of tangent. It just means that it's out of phase by 90 degrees. All right. If you were to draw the wave that these pictures would produce. All right. They're complements of each other. Think 90 when you think complement, like supplement is 180, complement is 90. Co is referring to that. Okay. The cotangent, which is COT. And then again, parentheses, because it's a function, would simply be this ratio that is tangent upside down. So if tangent is opposite over adjacent, then cotangent would be adjacent, and I'll put this in green maybe. Adjacent over opposite. Whatever the number is of that respective side of a right triangle would now be the numerator, and whatever the opposite number would be the denominator. Can you see that? I think you can. And if not, I'll darken it. I don't know if green is showing up too good, so I'm going to do this. Cotangent. Adjacent over opposite. Okay. The next one is secant. I'm going to unfortunately have to erase my picture, but before I do, let me just give you an idea where this phrase secant comes from. A secant is another line in respect of a circle that would go, if it was drawn a little bit nicer, through the center. Say that that's the center here. And touches on two portions of this circle as well. If a tangent only crosses or touches a circle in one place, a secant is a type of line that would touch in two places, not to be confused with a sine. What's the difference? A chord would not have to go through the center. All right, a secant would go through the center. Anyhow, what you see forming here, potentially, is that there is a right triangle formed by all this mess, right, in the middle here. If only my black wrote a little bit darker. You know, draw it like this. If you took a chord and drew it through here, and then this is superimposed upon a coordinate plane as the center of the circle, you see that there is a triangle, a right triangle formed in the process. Right? Anyhow, that is what the phrase sine, tangent, and secant are alluding to. Right? Basically, these lines drawn onto a circle, and the circle itself produces a triangle in the process. Well, the drawing produces a triangle in the process. Let me erase this. Okay. Just a couple more, and then we'll shift gears and we'll talk about the perspective of section 7.3 again. Number 5 and number 6. Alright. Secant is the next one I mentioned. Secant is abbreviated SEC, that makes sense. Right. And again, it's a function, so you see parentheses, and then whatever the angle is, of which it is dependent. Again, I feel it is practical. I don't like how messy that is. Just duplicating what I wrote here a little bit nicer. It is practical to learn these trig functions in this particular order, and especially the first 3, because if you know the first 3 via Sohcahtoa or whatever it means, all right, you could figure out what the reciprocal functions would be. Right? Tangent and cotangent are reciprocals of each other. They just have this ratio flipped, right? And then it's like that outside, right? And then a little bit further. Cosine and secant are reciprocal functions. So if you know that cosine is adjacent over hypotenuse, and secant is hypotenuse over adjacent. Remember, they're just a number that would sit here and here as part of the dimensions of a right triangle. Last one is cosecant. Cosecant, again, has the co prefix, all right? This means that it is a complement of secant. It's out of phase by 90 degrees, because this refers to waves, all right? Is abbreviated CSC. And again, theta is the variable on which the function is dependent. Sine and cosecant, these two on opposite ends of the spectrum here, are reciprocal functions. So if sine is opposite over hypotenuse, then cosecant is hypotenuse over opposite. Okay. Again, this is the first 3 are imperative that you try to memorize that information, because if you do know those 3, you can figure out what the remaining 3 ought to be. And do it in this particular order, right? This being the first, this being the second, and the third. And then the things that kind of sound alike, tangent and cotangent, the complements of each other, are where sort of the mirror exists, right? You can think of this scribble as being a mirror, right? And the ratios would be flipped. Okay? Secant, cosecant. If you are in section, let's see, 7.3. 7.3 is when you have standard position. Let me put this here. Standard position of your angle which forms your triangle. Right, at the origin, something like that, on a coordinate plane. This is the top part of the circle, if you will. Here's my little right angle box. All right. If you have something, maybe I'll erase this and put this here for a moment, just for reference. If you have a coordinate plane, x, y, and you have a circle superimposed upon it, and a triangle drawn into it, like this, and it would always be perpendicular to the x-axis and the vertex at the origin, 0, 0. This is a letter frame. Put this down just a wee bit. There we go. This triangle here, right triangle, with a vertex at the origin, riding along the x-axis, and it would be perpendicular to the x-axis, even if it were upside down over here. All right, always. If it is on an xy coordinate plane, and this is a certain amount x, and this is a certain amount y, naturally. All right, this still being part of a circle is still referred to as R. If that's a little too faint, this is a lowercase r for radius. All right, we can translate the sine, cosine, tangent, trig functions into these dimensions x, y, and r respectively, rather than saying opposite, adjacent, or hypotenuse. Now you might say, well, why don't we just do that to begin with? Because this is for a triangle in any orientation, Sohcahtoa, which is practical. All right, this is the ratios for sine, cosine, and tangent, and so forth, when the triangle is in standard position. That is, it's drawn into a picture like this. All right, so it's oriented in a very particular way. All right, perpendicular to the x-axis, vertex at the origin, standard position, if you will. I'm going to write this here, and I'll put it in script. And it doesn't have to be, but just to sort of distinguish it. It's sine of theta, cosine of theta, tangent of theta. This is moving around a little too much. And again, still our theta angle in here. So theta, theta, theta. What technically would be, I'll make this a little bit more obvious. Easter egg. What would technically be the sine opposite of the angle in this corner here would be a y value. So that is how you would write that in standard position. It would be referred to as y as opposed to opposite of the angle. It means the same, it's referring to the exact same place. It's just, again, a different perspective of this. All right? And in place of hypotenuse, which is always the longest side, which would be stretching from here to here in the drawing, we're calling it r. Like that. This is more practical, right, for problems that you see in section 7.3. Y over r is sine. For cosine of theta, let's see. Instead of referring to it as adjacent over hypotenuse, notice where what would be adjacent to the angle here would be x in the drawing here. We'll call it x then, right? And the hypotenuse consistently will still be the radius, or still be this dimension here. Get a little bit more flair than it needs. Tangent is opposite over adjacent, so instead of calling it opposite over adjacent, we'll call it y over r. Pardon me, y over x. Okay. And the 6 trig functions that follow it would just be naturally, again, the reciprocals of those fractions, those ratios flipped. So I'll erase this, and then I'll duplicate that. Let me complete this line, and this one, and this would technically be the end here. There are other reciprocal functions on the bottom of this. I'll give them to you, but I don't think they're actually immediately important. Let me finish this first. Alright, remember, if tangent and cotangent are reciprocals, cotangent, secant, and cosine are reciprocals, and sine and cosecant are reciprocals. And this is what this would translate to. Theta, theta, theta. Cotangent and tangent again being reciprocals, this fraction flipped upside down would be x over y. Secant and cosine are reciprocals, so this ratio would be r over x. Cosecant of theta and sine are reciprocals. So if it is y over r, it's r over y. Okay. Again, know these 3 by heart, but they correlate to in standard position now. It is vertex at the origin, perpendicular to the x-axis at least. Because then you could determine what these ratios actually are. You're building a reference. That was the whole point of the exercise, of getting you to write this. Right? But it is also helpful to memorize it in the long run. That's the strategy. You want to internalize some of this information. Right. I'll give you this stuff at the bottom, but I don't think it's immediately necessary. There are, if you notice on the same sheet, it says reciprocal functions. I've alluded to that already anyhow. And then the cofunction identities. Let me just stand away from this, make sure everything is copacetic. Looks good. Relatively speaking, right? It's a big sloppy mess, unfortunately, but the information is correct. That's the most important thing. Maybe just for reference, I'll give you these other things. But I don't think, I had designed this for the textbook problems, which are a little bit more difficult, I think, than my open math homeworks. But just in case, I'll give you this. Okay. You see on the bottom of the paper it says reciprocal functions and cofunction identities. Sine and cosine being what they are, and tangent. Sine of an angle, I'm going to not bother writing the parentheses, is equal to the cosecant of the same angle. Right. Cosine of theta is the reciprocal of secant, as mentioned, of theta. Same name. And tangent of theta is the reciprocal of cotangent. You could switch these and it would still be true. You could switch these and it would still be true. You could switch these and it would still be true. Again, to be fancy, you might put parentheses, but after a while it just becomes superfluous. As for the cofunctions, remember the co-prefix that is thrown into cosine, cotangent, and cosecant is referring to them being out of phase by 90 degrees, which means that if you were to subtract the angle of 1 and 90 degrees, they would be equivalent. Here's what I mean. The sine of theta is equal to the cosine (90 degrees minus that angle). Cosine is the same thing, just backwards. Let's see, secant. Let me do that because I think it's worse. If you had this as well, cosine, difference of 90 degrees as well. I'll make this red. Secant of theta is cosecant out of phase by 90. Whatever the angle number is, you subtract from 90, and this vice versa. And then the last ones, let's see, tangent of theta is cotangent out of phase by 90 degrees. Out of phase is just saying shifted. When we get into actually drawing the waves, you'll notice that it's basically a wave that's scooted over horizontally or backward or forward. Let's see, make sure that's correct. Good. All right, last one. Cotangent is this backwards, somewhat backwards. It's out of phase by 90 degrees. Okay. Okay. Cotangent. Good. All right. Again, it's probably overkill to have this. And in the long run, usually what happens when you take a trigonometry class is that they establish very long tables of information like this for reference. I like to make a person write things only for the reason that I know that if you physically write something, it helps you remember it. The mental exercise, the experience of actually physically doing something is you're more inclined to remember it. Okay. All right, now we get to the more or less normal portion of the show here. Let's see if that props up good. Which is finally getting a satisfying answer, not just memorizing fun facts about stuff. Facts. Sorry, colors are getting dried out here. Okay. One thing you'd be asked to do is to evaluate. Okay. Trig functions. And you'll be given a picture normally. So you'll see triangle oriented in any position. space. Kind of a free floating triangle, doesn't have to be on a coordinate plane. And just to test how well a person grasps the concept of Sohcahtoa, that is opposite over adjacent and so forth and so on, let's say that we orient the angle in question up here rather than in the corner here. And I'll give you these dimensions. Here's the right angle. Here is the 5 dimension here, and a 4 here, and a 3 here. A couple of things you could sort of talk yourself through right off the bat. Which one of these is the hypotenuse? The hypotenuse is always directly across from the box. So I would look for this immediately. It's a beautiful green eye. All right. Looks like a bug actually, but hey, whatever. Everyone's a critic. Just look for the box and then note that the number across from it would have to be the hypotenuse. Okay. That'll get you started. Now, if you're just going to do the first 3 trig functions, not to go crazy, let's figure out what the sine of theta would be using these numbers. The cosine and the tangent. All right. Remember Sohcahtoa. I'll put this up here. Sohcahtoa, which sounds like some kind of math cult, right? Join my cult. You already are. I guess technically under duress, right? Have to beat the drum. Dum, dum, dum. All right, roll, you students, you roll. All right. Get that hand. All right, back to work. All right. Let's look at this angle now, because this is what the trig functions are actually referring to, whatever number would be there. The sine would be opposite over hypotenuse, because of so, right? Opposite of the angle oriented here would be 4. So it would be 4, and the hypotenuse we've already established is 5. So whatever the angle number would be here would be the equivalent of 4/5, 0.8 as a decimal if you like. Cosine. Cosine of the same angle is adjacent to the angle, which would be this number here, immediately next to it rather than opposite of it. All right. So it would be 3 over the same hypotenuse, which we've already established is 5, 3/5. And tangent would be opposite over adjacent. So it would be 4 over 3. Okay. All right. We could also use Sohcahtoa, the perspective of trig functions, 7-2 perspective of trig functions, to find missing side lines. Let me erase this. Find missing sides of a right triangle. And again, I'll just draw a sort of free-floating right triangle to emphasize that this is for any orientation of the triangle. It's not really very nicely drawn, I'm sorry. You get the idea. Gotta be a good guy and put the box here, making it a right triangle officially, and then fill in a little bit of information. Let's say that the angle given is 30 degrees. And we have dimensions, the only dimension given is being 7. A couple of things I would do up front, all right? Identify the hypotenuse first. Okay. box is oriented here, then the hypotenuse would be whatever dimension is directly across from this box, which would be here. This is the hypotenuse. Okay. If the angle is oriented here, then the dimension that is directly across from here would have to be opposite officially. Okay. And that leaves us with adjacent. This would have to, by sheer logic alone, have to be the adjacent side, right? Which is unknown, as is the hypotenuse unknown. The only thing that is for certain in terms of side dimensions is that the opposite of the angle is 7. We can use basically trig functions to calculate what the dimension would be here and what the dimension would be here. All right. I'm going to list the 3 that we should know, all right? And then we'll strategically choose the one that is relevant for us, or maybe choose the 2 that are relevant. All right. Sine of theta, cosine of theta, and tangent of theta. Remember what they equal. Sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse. And tangent is opposite over adjacent. This was a little bit neater. Okay. Anyhow, if you want, you could fill in the one dimension that we actually have, that is the angle measurement. So you could insert 30 in here, understanding that it is in degrees. You might wonder at this point, well, what about radians? You know, you mentioned that last time, buddy. There are some times when you have to do something in radians and sometimes when you have to do things in degrees. If it's given to you in degrees and they don't specify any change, leave it alone. Anyhow, look again back at this triangle here. All right, let's fill in the information that we have. All right, we know 7 is an opposite dimension, so we have a 7 here and a 7 here, and everything else is up for grabs. All right, remember, when you solve something algebraically, you need the majority of information. Like if you have 4 parts, you need the majority. You need 3 out of 4 things to infer algebraically the 4th thing, right? Or if you know 2 out of the 3, all right, pieces. That's kind of the situation that you have here, all right? If you want to calculate the hypotenuse, we'll start with that maybe, then you have to look at your choices, door number 1, door number 2, door number 3, and identify which has the most information and also simultaneously involves the thing that I'm looking for. Starting with hypotenuse. I would say that this would be a good choice to start with, right? Perhaps. Because even though the hypotenuse is the denominator of this ratio, if you will, all right, we can rearrange this to solve for the actual number value, right? So what I'm going to do is I'm going to just kind of do some work over here using this. If the sine of theta is equal to 7 over the hypotenuse, and I really want to solve for hypotenuse, that means that I'm going to have to rearrange this equation algebraically. It won't be too bad, right? It conforms to the usual shtick of, well, in order to rearrange the parts of an equation, I'm going to perform the opposite operations. It's just that I'm going to have a word or an abbreviation for a word to rearrange. Right? If it's understood that this is being divided here, what is the opposite of dividing by hypotenuse? For the sake of justifying moving it, you do multiplication. You would write hypotenuse weirdly over here, and then remember, to get away with this legally speaking, whatever I've done here, even if it's for the sake of a cancellation effect, I'm obligated to do here. All right? Which means that I have this now. I have the hypotenuse times what was there already, sine of theta, sine of 30, equals now sad, lonely 7. If again, I'm trying to solve for hypotenuse, I gotta get it alone on one side. It did require this first step of moving this. Now I'm gonna move sine of 30, right? If it's understood these things are being multiplied because they press together, and to justify moving it from where it is over to the opposite side, I'm gonna divide by the sine of 30. It'll cancel whatever decimal it is, right? And then in order to get away with it legally speaking, if I did it here, I'm obligated to do it there, to the opposite side. Basically, the hypotenuse dimension, which we are looking for, will be equal to the outcome of 7 divided by the sine of 30, right? Which is something that you would type into your calculator. Okay. Let's see. If you, just to go through the exercise really quickly, if you have your graphing calculator, right, your TI-83 or 84, right, a couple of things. I'm going to zoom in on this. You may, if it isn't fresh out of the box, you may have to switch the mode. So let's say hypothetically you turn this on, right, and you want to do this calculation of 7 over the sine of 30. All right, let's make sure that it is in degree mode because it was, we had our dimension of an angle in 30 degrees specifically. There's a button up towards the top here that says mode. And if you press that, you'll see a couple of choices. All right, what should be highlighted is it's in normal, and then degree is highlighted, so I don't have to actually change the function. If it, for whatever reason, was maybe somebody had used your calculator before you, you want to switch this, just scoot the cursor down to radians and then either press enter to choose that instead, or scoot it over to degrees and press enter to make sure that it's in degree mode. Okay, it's something that you have to unfortunately sort of toggle back and forth as you do your problems. Right? Some problems require radians and some pi radians. Well, it is actually complete radians, it's a decimal. All right, or degrees. All right, we want degrees right now. So you would hit 7, all right, and then hit division. And then you could just press, notice that you have your trig function button, sine, cosine, and tangent already here. The sine of 30, right? You can go be a good person and close the parentheses and hit enter, right? And there it gives you your dimension, right? Okay. All right, so what I'm getting here is 14. Hypotenuse is equal to 14. I'm going to slowly but surely fill in my picture then. Now I have 2 dimensions. In theory, I don't need to go through this exercise again, right? I don't have to rearrange any trig functions in order to acquire the last missing thing, which would be adjacent, right? But you could, as an alternative, I don't want to drive you crazy, but just remember, you have choices. Right, and it gives you freedom, right? When you realize that you have choices, you could do something one way versus another, and you only know with experience which is maybe the most efficient or what is most comfortable for you. If you wanted to, you could have went with this incarnation of a trig function first, right? Why? Because it had the majority of information as well. The difference would have been that this solved for adjacent first, rather than solved for hypotenuse first. Anyhow, you'll get a decimal number, I want to say, in that case. To prove a point, here's what you would get. Do the work here. If I went ahead and started with this tangent of 30, and to make this a little bit quicker, tangent of 30 would have been equal to the information that was filled in, 7, over adjacent. In order to solve for adjacent, I would have had to manipulate it manipulate the equation via the process of algebra, that is performing opposite operations. The opposite of dividing by adjacents would be to multiply by adjacents, whatever number it would have been, and do it to both sides for the sake of balancing. Okay, there would be a cancellation effect here, 7 would be left over, and then I would have to move tangent of 30. Opposite of multiplying by tangent of 30 is to divide by the tangent of 30. There would be a cancellation effect, and then it would be the denominator here, tangent of 30. All right. Adjacent would be A dj is equal to this ratio. All right. You would type this into your calculator. All right. I'm just curious what it would be. All right. Let's see. If you type 7 and then division of the tangent of 30, close parentheses, you see that you get a decimal number, 12.1, all right? Unless they specify, hey, round it to the whole number or round it to the tenths place, let's just say it's about 12. Tripping off my shoelace here. Excuse me, I have to suddenly tie my shoelace. The math gods are angry. Anyhow, this is approximately 12, right? Which means the dimension here, I'm going to put squiggle equals, is about 12, all right? If you notice, all right, again, you either had this choice or this choice to start with, right? When you do, if you wanted to, after we had done this one, go directly to this ratio, we could have gotten the same answer. All right. Let's see. We could have manipulated cosine instead. Yeah, I'll erase it here to prove a point. Say that we went for this immediately after having solved for hypotenuse. Could have said, okay, cosine of 30 is equal to adjacent over hypotenuse. I would only have to manipulate this in one step rather than in two. That is, multiply by hypotenuse simply to move it over here. And then insert the number 14. So what I would end up having is that 14 times the cosine of 30 typed into my calculator should in theory produce the same number, 12. Let's see, 14 times cosine of 30, and then you see it's the same exact numbers, 12.1, 12.1. Again, I can't stress this enough, there is often more than one way to do something in mathematics. Do what you feel most comfortable with, but then be open-minded, right? Realize that you have choices, and then maybe in some instances, some problems, it would be better to do it one way versus another, which you only know with experience. Okay? All right. Let me give you another quick diagram and 1 or 2 more problems, and then I'll let you go. We're at the hour 18 mark. Okay. There are 2 special right triangles, famously, which are good to have as a reference and also to memorize in the long run. Let me give you a diagram to summarize. Two special right triangles. They have dimensions that are consistently true. And it would be good to use them as a reference. All right, there is famously the 30 degree, 60 degree, 90 degree right triangle. Notice that there's a 90 in it, so it absolutely must be a right triangle. And then there's this. The 45 degree, 45 degree, 90 degree triangle. Again, absolutely must positively be a right triangle because it incorporates a 90-degree angle. They add up to 180 if you wanted to really obsess over the fact that the triangle must be 180 degrees total. Right? Anyhow, they look like this. We're just going to draw them in more or less the normal standard position. Here's our little 90-degree angle. And I'll do this one here. There's our 90-degree angle. Okay. The dimensions in respect, if this is 90 here, let's say that this is 30 and this is 60 here. I don't know if you can see that, so I'll make it a little bit more obvious. 60. The dimensions of the side here, here, and here are consistently true for a 30, 60, 90-degree triangle. They are 1, the square root of 3, and 2 for the hypotenuse. Even if you have a triangle that is not these dimensions precisely, but still incorporate 30, 90, and 60-degree angles, right, they would simply be a multiple of these dimensions, right? Anyhow, keep this as a reference, right? 1 would be riding along the side where 60 is. Let's see if I can emphasize that. The dimension of 1 would be riding along the side where 60 is. Right? The square root of 3 would be riding along the side that is the 30-degree angle. Right? Even if this was oriented, the triangle itself, a little bit screwy. Right? Look for the 30, know that there's a square root of 3 adjacent to it. Look for the 60, know that there's a 1 adjacent to it. Right? And the hypotenuse would be 2. If, on the other hand, you have the 45, 45, 90, these are the dimensions. 1, 1, and the square root of 2. Okay, the hypotenuse is the square root of 2. The insides of the triangle would be 45 here and 45 here. Because of those identical angles here, these are what the dimensions would be, 1 and 1 respectively, right? And the square root of 2. Right. So you really, this one is, in theory, the easier one, because it's only 2 numbers that you have to memorize. But adjacent to 45 would be 1, adjacent to 45 would be 1, right? And the hypotenuse is the square root of 2 as opposed to regular whole number 2. Now, knowing these allows you to evaluate trig functions or determine the coordinates on a unit circle. That's really the point of this. Knowing these helps determine the coordinates on a unit circle. Okay, remember, if you have a unit circle, I'm going to try to draw this neatly. A right triangle can be drawn into the unit circle here, like so. And the coordinates, which are normally x and y, would be the cosine and the sine, respectively. That's a little bit small, let me make it larger. X is cosine y is sine. All right, of whatever the theta is. If you want to generalize, I'm just going to use theta. All right, anyhow, ratio, remember what cosine and sine are, they're ratios, right? So if you had a ratio of these dimensions for sine, which is opposite of 45 over the hypotenuse, all right, you're going to naturally get a decimal number, right? Just to show you. 1 divided by the, let's see, square root is secant 2. We would have to rationalize the denominator, but I'll get into that another time. 0.707, something that is shy of the amount of 1. That's not a coincidence. If you were comparing this to a unit circle, the radius should be 1, right? But these dimensions will be ratios, so it will be some fraction of 1. The y dimension is a ratio. The x dimension is a ratio, specifically the sine ratio and cosine ratio. Okay. All right, there is any point to this. This is a diagram I would have copied and handed to you. I'm going to make it available naturally in Canvas. These are a reference of what the coordinates x and y would be for famous angles like 60, 45, 30, 0, and so forth and so on. You would need to know 60, 45, and 30, right, as a reference when you would be trying to calculate these coordinates. You'll notice that the only difference between them, right, for things that correlate is 30, right, and here is 120, 150 rather, is that you have a negative dimension for the x. That's only natural, right? Because where would you be? You would be in the second quadrant in theory, which has x that are negative numbers, right? And if you were down here in the third quadrant, notice that you have both negative dimensions. Anyhow, I would print this, right, and keep it as a reference. When you're doing your calculations because you want the experience, don't cheat, you know, like you want to do it legitimately, because the experience will help you absorb the material, all right? But to validate your answer, if you feel iffy, all right, know that you have a resource that will help you. Right, to go, yes, I was correct. All right. Hopefully that wasn't upside down. What keeps messing me up is my camera is the mirror image of what it should be while it's recording. I don't know why it's like that. Yeah, let's do a couple of examples. Sorry I'm using blue so much, it's just that it happens to write fairly well. Let's say that you had as an example to find the cosine of an angle theta, right, given that the sine of the same angle theta is this ratio, 3/7. And that the angle is in quadrant 2. What you should always do for these types of problems is draw a picture to summarize the instruction. I tried to make it as minimally verbal as possible. All right, you're looking for this. All right, which you know means that it's going to be a ratio. But in order to get that ratio, the numerator and the denominator respectively, you need to calculate what the numbers ought to be, adjacent and hypotenuse respectively, if you drew a triangle. You are given this much information, right? And they're demanding that the angle that they're talking about, which is what theta is, all right, happens to be in quadrant 2. So let's draw a coordinate plane, or you know what, I'll use my sheet that I have here. see if I can get it in frame. That looks pretty good. Okay. Here, all right. Remember, this is our x-axis, this is our y-axis. Right? These would be positive x's and positive y's. This is negative x and negative y, respectively. This is quadrant 1. This is quadrant 2. In standard position, normally, even if we were using any type of right triangle superimposed on a coordinate plane, would normally be drawing it in quadrant 1, right? In this particular problem, they're demanding that you draw something, a right triangle essentially, in quadrant 2. So you're basically going to limit your focus to here. All right, just a couple of pointers here as well. Remember, draw perpendicular. That's what this symbol is. To the x-axis always. Even if the triangle is upside down, make sure that you connect your triangle vertically somehow to the x-axis. Okay. All right. So if I drew a triangle in quadrant 2, that would be here. I'm just going to randomly draw a right triangle. It may not be proportionate correctly, right? But it would be something like this, right? This is a right triangle that is in quadrant 2, which means it would have to be oriented like this rather than upside down, which that would make it quadrant 3. And I'll draw the bottom leg here. And this is officially a right triangle. So it has that little 90-degree box in one corner. I'll erase unnecessary information. Okay. So we're working here, and we'll assume that our angle theta is in this corner. You could always make that assumption. Okay. We're going to start with the sine now and pluck it apart. If sine of the angle theta is 3/7, let's fill in the dimensions appropriately. According to Sohcahtoa, right, sine of theta is opposite of the angle over the hypotenuse. So I'm going to appropriately place this 3 in respect of the angle that in such a way that it is opposite of this angle. That would make the dimension this way 3. Make it a little darker. Forgive the grid lines because it's out of proportion. I'm just using it for the axes, really, this picture. All right. The hypotenuse would have to be this dimension this way, 7. If we are going to calculate the cosine of theta, all right, the picture is going to be important, all right, because the picture will basically decide whether something is negative or positive. But we still need to know Sohcahtoa, right? Cosine is what? Adjacent over hypotenuse. So if I need to, I can borrow whatever information I have. They'll have the same hypotenuse, the cosine and trig function, the cosine and sine functions. So I'll have a 7 here. Right? But I would need to calculate what the adjacent dimension is. Right? The adjacent dimension in respect of this angle here would be down here. Right? And since it happens to be where? In quadrant 2, what is the nature of the x dimension that is known as adjacent? in this case? Is it a negative or a positive? All x's in quadrant 2, and technically also in quadrant 3, are negatives. So even if I do some kind of a calculation, I have to make sure that I have a negative number that is sitting up here in my ratio to answer this question. All right. Now how do we do that? Well, we're going to go back. I'm going to have to erase a little bit. We're going to have to go back to good old Pythagorean Theorem. The traditional perspective of a right triangle. Put this in color. Remember Pythagorean Theorem, right, which is famously a squared plus b squared equals c squared. If you want to adapt the Pythagorean Theorem to the dimensions that would be generalized in this particular blue right triangle here, we're looking for an x, all right? An x dimension in the Pythagorean Theorem would probably be the bottom of this, all right? So I'll put it in the b position. The hypotenuse, which is c, and this is a leg, and this is a leg, in our case here would be 7, all right? And the a value, a is an altitude if you will, would be 3. So I can fill in this much information. I'm just going to have to identify the bottom here, which is normally b in the formula coincidentally, as x, because that's the thing that I'm looking for. And I'll go through the motions, the algebra, the rearranging and the arithmetic, all right, to figure out what x actually is, and then make sure that I make it a negative, because it would be here. Okay. So, let's tidy up one side before, do the arithmetic before you do the algebra. 3 squared is 9, right? And over here, 7 squared would be 49, and this is x squared still. And I'm going to rearrange this. I'll take this out just to make it less distracting. And go through the motions, right? If it is assumed that this dimension is 9, and it would have to be, right, anyhow, I'll subtract to justify moving it from here to here, and balance it as such. The 9's cancel, x squared would be left over. 49 minus 9 would equal to 40. And we're not finished, remember, until we get this down to just x, whereas in the formula it's x squared, right? So we're going to employ the opposite operation of squaring, which is square root, right? And remember, if you did it on this side, we're obligated to do it on that side as well. All right, what happens naturally is there is a cancellation effect. By design, this cancels this, leaves us with just x. And then you have this. Now you may feel a little sketchy because you haven't done it in a while. But this is the correct answer, and yeah, you could type it into your calculator, the square root of 40, and get whatever the decimal equivalent is. It would be more ideal, right, if you just factor it. More ideal if it were factored, right? The product rule of radicals says that you could split this, right, into 2 factors, things that multiply together that make 40, and they'll still each be underneath a radical symbol. What you want to do strategically is factor this into something that is a perfect square, because if it is a perfect square, it will escape the radical. Right? And ideally it's the highest perfect square, right? And then maybe something that is just left over that would be impractical to factor further. Like it sometimes is a prime number like 2 or 3 or 5, and other times it just happens to be composite like the number 6. 6 is something that in theory could be factored further into 2 and 3, But it wouldn't be practical to do that because neither of them will give you a perfect square. Nothing else will escape a radical. Anyhow, try to conceive of two numbers that multiply together that make 40, right? And one of them being a perfect square. Right? Famously, it might be 4 times 10. Right? In theory, if you started with something else like 5 and 8, you can get it to this point eventually, but again, the strategic ideal situation is highest perfect square. So I'm going to go with 4. Right? Anyhow, I'm going to write this here. This escapes the radical by design. What's the square root of 4? 2, right? So you have 2, and then you're stuck with the square root of 10. Right? If you were to factor that further, you'd get stuck with 5 and 2, which doesn't help. So you leave it alone. This, although it is kind of inhuman and not especially satisfying, is the answer as a result of this calculation. Now, in theory, because we're dealing with a square root, a positive or a negative is possible. In this case, which one do we want? We want a negative because it's in quadrant 2, right? Anyhow, going back to our ratio up here, which was the actual problem, we actually wanted to solve for the cosine of theta. We used 7 to fill in the void for hypotenuse. Now we're going to put this number, right? Negative 2 square root of 10. And that would be our solution. And in our drawing, if you like, you can put this here, negative 2 square root of 10. All right. Let's see. Let me do one more problem. And I'll stop at about 10 minutes on the normal conditions anyway. Try this. Right, if they say find the exact value of sine or cosine. Basically what that is code for is it means don't use your calculator to get a decimal, because even though it's very tempting, right, especially nowadays, to gravitate immediately to our calculator to get an answer that is very precise, right? The truth of the matter is an exact answer is something that may incorporate a square root. And it actually is a better answer because it preserves all of infinity. The infinity that granted we're not actually looking at, like the square root of 2 is 1.41 something into infinity, and nobody really likes to be bothered with that. But if we don't use a calculator, then we're not rounding anything, right? We would prefer to have something, believe it or not, that still incorporates the radical, all right, because it preserves all of infinity. In theory, it's the exact answer versus a truncated or a rounded answer. All right, so here's an example. Let's say that you are going to find the exact value of sine or cosine in this situation. Let's see. Do I really want to put that back? Let's see. No, I'll just draw a diagram, simple here. Here's X, here's Y. And imagine a circle superimposed upon it like so. And we're given this. The cosine of 150 degrees is equal to such and such number. You can immediately, of course, especially if your calculator is rigged as such, go to your calculator, turn it on, of course, clear this, hit cosine, type 150, and then you'll see the decimal equivalent. Negative 0.8, I'll put this close, negative 0.86602, whatever it is, into infinity. All right. That is a little bit more natural for us. We like decimals, human beings, especially in the culture that we live in, because even money is in decimal, right? But if you were going to use this number as part of some more complex calculation, let's say you were in engineering or you were in science, right, or maybe in business math, I suppose, you would have to round it, right? And that will unfortunately change what was already technically perfect into something less perfect, right? We would rather have an exact answer, not to belabor the point. Anyhow, we're going to not use our calculator. We're going to get the exact answer, and then I'll use the calculator to prove that it is really more or less the normal situation. What we calculate is validated by this only. Okay. Anyhow, when you're given a problem like this, and again, you want the exact value of this, right? Draw a picture, all right? And remind yourself, what are the endpoints in terms of degrees? This is an x and y coordinate plane, but I mean, if this is 0 degrees, and remember we read counterclockwise to read angles. This would be 90, and this would be 180, and 270, and back to 0 would be 360, a complete circle. It would be good again in the long run to memorize this information. But if you're only going so far as 150, where again is that coincidentally going to plop us in terms of a coordinate? Quadrant 2, right? Technically speaking. Because to go from 0 counterclockwise to 150 would basically, I'll put this on the edge of the circle if I'm a little bit more strategic here, would have us here, right? If you took out a protractor and measured 150 degrees, it would be somewhere between 90 and 180. Right? We know that 90 is exactly this vertical dimension here, and 180 is exactly this horizontal number here. All right, so 150 by sheer logic alone would have to be somewhere in between. Right? If I drew the picture a little bit more precisely, it probably would be favoring the 180 a little bit more than it is the 90, not exactly in the middle. All right. But anyhow, look what we have. We have the beginnings of a right triangle. Right, and just to re-emphasize the point from before, always draw right triangles perpendicular to what would be the x-axis. Okay, so to complete this drawing, I'm going to draw a vertical line down to the x-axis, and now I have a right triangle. Okay, this information, all I needed this number for really was just to orient it into the correct quadrant, right? Why? Because that makes this a negative x, and that makes this a positive y. Okay, and R is what R is. All right, now moving on. We need a reference angle. We're going to basically use reference. All right, either 30, 60, 90 triangle, or the reference will be the 45, 45, 90 triangle. Why do we need that? Because we know, oriented in the typical fashion, that if this is 30, 90, and 60, then these are the dimensions, and they will correlate to this triangle. We'll just have to change the orientation of this. We'll make it negative instead of positive. If we have a 45, 45, 90, and it's 1, 1, and the square root of 2 instead. What is important again is just convince yourself adjacent to 30, square root, pardon me, adjacent to the 30-degree angle is the square root of 3, right? Adjacent to 60 is 1, right? The 45s are 1, and the hypotenuse is square root of 2 versus whole number 2. Anyhow, let's figure out what the angle that would be in here should correlate to, either this situation or this situation. In other words, what is the difference? What is 180 minus 150? What is the difference? It would be a 30-degree angle. That means that it would be most appropriate to borrow information from this reference rather than that reference. Okay. So therefore, let's delete out anything that is distracting. We don't need that. And maybe just enlarge this. This is now, having gone 150 degrees, really representative of a 30, 60, 90-degree triangle. Then that means that the dimension, although it would be negative here, would be whatever the dimension is normally adjacent to 30. If normally the dimension adjacent to 30 is square root of 3, what I'm going to have is negative the square root of 3. And what would be adjacent normally to 60 is positive 1. This is still oriented in the positive sense. So this would still be positive 1 here. And then the hypotenuse would be 2. Now, we're going to fill in opposite, adjacent, whatever it happens to be, specifically for cosine, and then plug in the numbers that are related. So if a cosine is normally the adjacent dimension over the hypotenuse, then let's insert what is adjacent to 150, which really is 30 by another name. All right. Negative square root of 3. Up here, sitting on top of hypotenuse of 2. That would be the value. Now remember what we got from before. Again, we're getting an exact value. This ratio is an exact value. Right? We could always do it with our calculator, but I would reserve that just simply to validate, to give yourself some confidence, right, as an afterthought. All right, here's what we have left. The cosine, let me get this out of view here. The cosine of 150 degrees is negative 0.866, whatever it is. If my answer is correct, and if my calculations are correct, right, that sounds so TV-like. If you took a negative square root of 3 and divided by 2, we should get this exact same decimal. So let's just validate. All right. Remember, when you're entering negatives, use this button down here rather than minus. So we're going to hit negative, go down here. Negative. The square root is behind square. So you hit the second, and then this, and then you can type 3. Scoot out of it. All right, now hit division for the fraction, and then put 2. And then press enter, and you see that we get the exact same answer. Negative 0.866 into infinity, whatever it is. All right. In this form, again, even though it is less human, a little bit more inhuman, this is considerably a better answer than the decimal, because the decimal would have to be rounded. Whereas if you took this ratio and inserted it into some other formula, whatever, it would preserve all of the decimal, all of the infinity, even though we can't see infinity. It's exact. Okay.
So my markers one by one.
All right, here we go. That's a dud. Okay. If you were to do sine, just coincidentally, for the same angle, you just write it underneath here. This is cosine. If you did sine of 150, you would end up using the exact same triangle and realize that the reference is 30, the reference angle. If sine is, under normal circumstances, opposite of the hypotenuse, then just incorporate these values. Right? Opposite of 30 is 1. Hypotenuse is still 2. So it would be 1/2 in that case. 1/2 is 0.5 as a decimal. Right, here's if you took your calculator, sine of 1 divided by 2, you see that you get 0.5. No, let's see. There's an error here, sorry. Yeah, 1 divided by 2. Why is it giving me funny numbers? Oh, I'm sorry. Yeah, that's normal. 1/2 itself is 0.5. This is the correct decimal equivalent. Okay. I'm typing in sine of 150. Sorry. Forgive me. Put the angle in here. 0.5, 1/2. Incidentally, if you would prefer the ratio form of something versus the decimal, you could always change that as an afterthought. If you press math and then scroll over to, I believe it's down the list here. No, scroll over to number, all right, and you can enter something in the style of a fraction by the choice down here. Or if you want your answer, the previous answer to be written in the style of a fraction. The first choice on the math, right, is to enter it as a frac. So choose that, and it enters it as 1/2. Okay. All right. Last thing is to find coordinates, and then I'll stop. I'm exceeding our time technically, but you can watch this whenever you have the time. Watch. Okay, if you are looking to find coordinates, ordered pairs. Here's an example. Find coordinates of the point on a unit circle at the angle given in pi radians. 7 pi over 6. In theory, you could cheat. This is probably one of the more famous angles here. But here's the process. All right. What I would do firstly is convert to degrees, because normally a person has the unit circle or, memorized according to 0, 90, 180, 270, 360, right? It would be good in the long run, admittedly, to know that this also means pi over 2, whole pi, 3 pi over 2, right? But there's quite a few pi radians in between, so it's a little less easy to memorize that stuff. All right, again, you have a reference, which again I would only use to verify our result. All right, let's do this by sheer logic alone. Okay, let's convert to degrees first. All right, here's an opportunity to take what is given, multiplied by the conversion factor that is appropriate, and rig it so that it cancels and spits out what we want. Let's see what I mean. This is more or less a review from last time. If we are given the ratio of 7 pi over 6, I'm going to put that here. It's already in the style of a fraction. I'm going to multiply by the appropriate conversion factor. Remember, there's only two. There's pi over 180, or there's 180 over pi. You want to choose the one that causes the cancellation effect of pi here. So I'm going to go with this one, where pi is on the bottom, because the natural consequence to arranging it as such would rig it to cancel these symbols, which means that your outcome would be 7 times 180, this would technically be times 1, and this would be in degrees, which is what we want. What's 7 times 180? I'm curious. 0, 56, carry the 5. 1260, this is awful. And 6 times 1 is 6. But if you divide them, it works out to be a pretty easy number. All right. 6 goes into 12 twice. 6 goes into itself once. And 6 goes into 0 times. So we need to go to the location, basically, of 210 degrees. All right. Again, you have this much memorized, that it is 0, 90, 180, 270. 210 would rotate from 0. I keep picking up the dud. 210 would rotate from 0 to some place in between 180 and 270. You can estimate, right? And again, it's always tied to the origin. So you have an angle that's 210 degrees, which is the equivalent of 7 pi over 6, right? Here's our reference to make sure. Yep, I'm going to cover up the coordinates for right now. But here's our reference. 210 is 7 pi over 6. All right, now we have to draw a right triangle as before. All right. And if in theory this is part of some larger circle, the right triangle would be, as before, perpendicular to the x-axis. This is still the x-axis. Just focus on this blue triangle that is formed by these superimposed drawings. Okay. Okay, there is now a right triangle because I drew it perpendicular this way. And it's going to have naturally, I'll get rid of the unnecessary information adjacent. A negative x dimension, because it would be in quadrant 2, again, for the x. And also simultaneously a negative y dimension, because it is now, this is also, this point here is in quadrant 3. The x is in both of them, but the y is in quadrant 3. And the end result, the dot here, the coordinates are respective of quadrant 3. Okay, now we're going to use a reference again. If going from 0 to here, pick up that dud, sorry. If you go from 0 all the way to here, 210, otherwise known as 7 pi over 6, let's figure out what the angle in here ought to be. All right, it's going to be either ideally 30, 60, 90 situation or 45, 45, 90. All right. How would we determine that? Subtract. Take 210. Right. Take your angle, all right, and either subtract 180 or take 180 and subtract your angle. Right. Basically, to give you some sort of a situation, consistent system for doing this. If the angle is greater than 180, then do this. All right, this will be determine the reference angle. If your angle is less than 180, then do this. Subtract from 180. All right, and this will be your reference angle. Okay. And our situation, 7 pi over 6 is 210. So this is this situation. It is far greater than 180. Difference of 180 and 210 is 30 again. Right? So the angle in here, and it's getting a little bit sloppy, so let me erase this. The angle that would be in here would have to be 30 again. Right? All right, I'm going to draw this triangle over here. I'll erase this other stuff. All right, just a little bit larger so it's easier to see. So we have basically this, and this is on the edge of the circle in theory, and we're trying to find what these coordinates are. Let's figure this out, okay? We know, as from before, that this is a negative x and a negative y because it is simultaneously in quadrant 3. So we can have a negative x and a negative y. But we're going to borrow information from the reference. So although it is normally oriented like this, (30, 60, 90, square root of 3, 1, and 2. We're just going to borrow that information and adapt it. The full 210 leaves us with an equivalent in here, riding along the x-axis and stretching into the third quadrant. All right, of 30. This is now perpendicular, so it's 90 on purpose, and this is 60. All right. That means that, again, by comparison, what is adjacent to the 30-degree angle should be square root of 3. It will just have to be negative because of where it is in relation to the axes. What is riding along adjacent to 60 in our reference, right, is 1. But because it is now part of this triangle pointing down into the third quadrant, this will be negative 1. Okay. So, what are the coordinates of this particular point that is in theory part of the edge of the circle? It's these dimensions. Okay. It is x is equal to the cosine of theta, and y is equal to the sine of theta. So I should say it is dependent upon these ratios. Cosine of theta is x over r, and sine of theta is y over r. I'm using the 7-3 perspective of this rather than the 7-2 perspective. Instead of calling something adjacent over hypotenuse, I'm going to call it x over r, radius, because this is a radius. Okay. Anyhow, we'll plug in the numbers that we have, and if we need to find any others, we'll use the Pythagorean Theorem. The x value for cosine, which is what this is going to be, let's see, negative square radius is normally 2. So I'm going to put a 2 here. Okay. And in this case, our y value is -1, and our radius is 2 again. They share that in common. Let me just verify here. Good. All right. If you're a little worried about, well, why is it that you didn't move the r, the radius, from here to here? All right. If I took the angle of 210 and multiplied it by 2 instead, it should produce this negative square root of 3, so negative 1.7 something. All right. The reason that I have to have it this way, that you have the adjacent over the hypotenuse, is because we're translating this from a unit circle. All right. So this ratio will produce a number that is something smaller than 1, because a unit circle has a radius of 1 and the reference has a radius of 2. The reference has a radius of 2, right? Whereas a unit circle has a radius of 1. Anyhow, it would be proportionate as long as we divide these two numbers. Okay? And that would be 1/2. Now, just to prove a point, if I took this, all right, you'll see that the number produced by this will be, in terms of its magnitude, will be something smaller than 1.0. Here is, it's going to be negative because of the location of it, but if you had the square root of 3, let me get out of this, divided by 2, okay. See that you get negative 0.866 again, all right? Something shy of 1 whole. How come? Because again, if we're translating this into a unit circle, the hypotenuse is the radius, and the radius is 1. So the x dimension has to be something smaller than that, because it can't be 1 exactly. It has to be something smaller than that to be a right triangle. All right. Similarly, the dimension here is negative 1/2 for its location, but it's the magnitude of 0.5 because it has to be something smaller than 1. A unit circle has a radius of 1. The reference has a radius of 2. We're just borrowing these dimensions because they would be proportionate as long as we use this calculation for cosine. And similarly for sine. Okay. Let's see. Here's our reference again. All right, we did the calculation. All right. At 210. 7 pi over 6 is really 210 degrees, and these are the dimensions: negative the square root of 3 over 2 and negative 1/2 respectively. Okay. Now, just to make sure you're not too sketchy about this, all right, realize, all right, that you're basically going to use this. When you have a coordinate of x comma y, when you're looking for x, all right, this is going to come from the cosine of an angle, and this is going to come from the sine of an angle. And since these themselves relate back to a ratio, it'll have to be an x value over the radius, and this will be a y value. over the radius. As long as these numbers are divided, it will produce a legitimate decimal number. Okay. Normally in a unit circle, the radius is just 1, right, which is why this is legitimately an x. Normally the radius is just 1, which is why this is just legitimately a y value, the thing on top. Okay. Alright, I believe that is it. Okay, so that is section 7.2 and 7.3 respectively. We'll be a little bit ahead of schedule next week. We'll do section 8.1 probably on Tuesday. All right. Anyway, do be careful out there. All right. I'll see you next Tuesday.